Welcome to this new lecture. In this lecture, we are going to talk about transient analysis. So basically, we are going to study what mathematical function produces those graphs we have seen in the previous lecture. Okay, so we have seen there are some functions like we have seen the capacitor's voltage starts from 0 and grows up to some certain voltage like 10 volt. And we have seen that capacitor's current, there is a spike, and then the current, basically the current starts to drop and ultimately goes to 0. Okay, so what graph does it, what mathematical function does it produce these graphs? Okay, so that's our target. So that's what we want to study, and that's what's called transient analysis. For example, let's start with the circuit we have been using for a while now, and we will be drawing the switch from now on. So I haven't drawn the switch, but I should have drawn from the very start. I haven't drawn them just to introduce to you in the simulation video, but from now on you should always draw the switch. Okay, so in addition to drawing the switch, we also draw an arrow like this. So this means whether we are closing the switch or are we opening the switch. For example, this means that the switch was open in the first place, but then we have closed it, right? So that's why we draw it like that. We are closing the switch. But if we drew the arrow like this in this direction, that would mean that initially the switch was closed and then we opened it. Okay, so there's a difference between the two directions. Okay, so the arrow here is very important. And you will also see that sometimes there is written like t equals to 0. What it means is basically we can turn we are basically turning on this switch exactly at time 0, and that could be anything else, but I'm going to keep it 0 for always going to keep it 0. Okay, so let's give the capacitor a value here, 1 microfarad. And what we are interested in, for example, let's say we want to know what's the node voltage of this circuit, right? So what's the value of VT here? How is the voltage here related to time? Is it like 2 times t, or is it like 3 times t squared, or is it like sine of t, or is it like something e to the power t, like something like that? It can be any function, right? So how is the voltage related to that time? That's what we are asking. So this is what is transient analysis. The voltage is now dependent on time, and as the time progresses, the node voltage will change, and we want to know what function that is. Okay, so that is not the only question. I can ask you many other questions as well. For example, if I ask you what's the current through this capacitor, or the whole circuit, really, same current will flow through everywhere, I can ask you that. Or I may also ask you what's the voltage here, VR, that's also a function of time. I can also ask you that. Okay, so all of these questions are transient analysis because they're dependent on time. Things I'm asking you that are dependent on time. So that's what transient analysis is. So at face value, this seems like a complicated thing to do, and in fact we have seen differential equations before. So we have seen derivatives, and so maybe you are thinking we have to do integrals and etc. But I'm going to make things very simple. I'm basically going to give you a shortcut formula that you can apply everywhere, and that you will apply everywhere and will get the job done. Okay, and we will not complicate the circuit. So the circuit will be very simple all the time. Very few amounts of elements will be in your circuit. Okay, and this formula will work almost every time. Actually, every time it will work. Okay, so what's the formula? So how does the function look like? What does this function look like? So let me give you the general formula. So if I ask you what will be x of t, so what will be x of t? So the function is basically x of the final x, okay, plus the initial x minus final x e to the power minus t divided by tau. Now you have a lot of questions, I understand that. So what do I mean by the initial and final x? For example, we are asking here the voltage of this node. So by that, when we write, so the formula here will apply something like this: Vf plus Vi minus Vf e to the power minus t by tau. So Vi here denotes the initial voltage, like the right at the moment you close the switch. What is the voltage? That's the question we want to ask. Okay, and this is Vi, the initial voltage, and the final voltage is basically if you close the circuit and wait for a lot of time. Okay, so you come back 2 days later or something like that, or mathematically speaking, infinite times later. What's the voltage? Okay, so that's your second question, and if you can answer that, you will get the Vi and Vf, and all you are left with is the tau. And the tau is also very simple. Tau is basically, tau is equals to R times C if we are dealing with a circuit that has a capacitor, and if we are dealing with a circuit that there is a inductor, tau will be L divided by R. So we will not have both inductors and capacitors in the same circuit at the same time. Okay, so in this course we will not use those kinds of circuits. We will either have capacitors or inductors, and there will also be just one resistor. Okay, so you don't have to really worry about anything. Just if you see a capacitor, use this formula. If you have an inductor, use this formula. That's this simple. For example, let's apply this here. Okay, so for this circuit we should have tau equals to R times C. Okay, because we have a capacitor here. The R here is 1 kilo ohm. So this is our R and this is our C, right? So we have 1 kilo ohm here times C, that is 1 microfarad here. And if we write it in the SI unit, so 10 to the power 3 ohm times 10 to the power minus 6 farads. And if we multiply them, we will have 10 to the power minus 3, and we will have seconds. So one thing I have not said is that if you multiply ohm with capacitance, farad, you will get seconds out of it. Okay, so this is actually just this is actually called time constant, and it has a unit of seconds. Okay, and I encourage you to actually check that if you multiply resistance with so ohms times farad is actually a time, and you can check that using the component equation for capacitance. Okay, so go back to that equation and check the units there. And for inductors, you will also see that Henry divided by ohm is actually second. So I'm encouraging you to check that too. Okay, so that's one thing, that we have one value. So the tau, we have already got the tau. Now we are worried about the initial and final voltage. Okay, so the initial circuit, what we mean, initial circuit. So I think we should always draw two circuits, an initial circuit and a final circuit. Okay, so the initial circuit will draw everything the same, and what's the moment you just, like, if you are closing the circuit, right at the moment when you close the circuit, that's what you want to draw. Like if you have 1 kilo ohm and you just closed this switch, okay, and you have that capacitor, right? So for you have, so this is like t equals to 0, just at the time you have or I think better t equals to 0 plus, you can write it right after the moment you have closed the circuit. Okay, so now we were interested in the voltage of this node, and since this is actually 0 volt here, and at the very start this will also have 0 volt here. Okay, why? Well, because you just close the circuit and it takes time for capacitors to grow the voltage, right? So the voltage will increase at a very slow state, very slow rate, and at the very start you will have a 0 volt there. Okay, so this is actually your VI. That's it. Like, this is your initial voltage, the voltage we were worried about, and this is the initial circuit, so this is your VI. So this is just VI equals to 0. That's all you need from this circuit. And for the final circuit, you also have the same circuit, 1 kilo ohm, 10 volt here, and 1 microfarad here. So what I want to do here is that actually the thing I have introduced in the first lecture about the capacitors and inductors, that eventually, so this is like the final situation, so this is like after infinite amount of time, this capacitor will become open, right? And we have seen that eventually this becomes open because there is a charge here, and we have seen that this because this is open, so there is no current, and we have 10 volts here, so definitely this voltage here will be will be 10 volts. Sorry, the color was not working. Yeah, so this is our final voltage. This is what we call final voltage. So the circuit ultimately stops at some point, and what that voltage is, that's your final voltage. That's it. That's all you need here. So this is your information, and here from this initial circuit, this is your information. So if we do if we write out the equation now, you will have V of t equals to V of f plus V of I minus V of f e to the power minus t by tau. So writing this out, we have Vf equals to 10 volt, right? This is 10 volts. So let's ignore the unit for now. We have Vi, this is 0 volt, 0 minus Vf again, so that is 10 e to the power minus t divided by tau. So we have seen that the value of tau is 10 to the power minus 3 for this circuit. So we write 10 to the power minus 3. And so just writing this simply, this is 0, so 10 to the we will have, okay, so 1 divided by 10 to the power minus 3, this is basically 10 to the power 3 or 1000, however you want to write it, doesn't matter. Okay, so you have 10,000 t. Okay, you have 1000 t. So this part I just wrote it like that. And if you actually plot this graph, this will look something like this. You have time on the x-axis and v of t, you are plotting v of t. This will start from 0 and creep up to 10 volt. Okay, so this is like the 10 volt line, and you will see that this gradually goes up to the 10 volt. It never touches that 10 volt line, but goes very close to that. Okay, almost touches it. Okay, so this is it. This is how the graph will look like. So this 10 minus 10 to the power e minus 1000 t. So this is our transient analysis. Basically you need to do these simple things. Now for example, let's see another thing, like maybe we asked what's the current to this capacitor, so what's the value of IT. Well, the equation will be exactly like that. Final current plus this will look very bad, initial current II minus final current times e to the power minus t by tau. So for this circuit we have already seen that the tau is 10 to the power minus 3, so nothing new there. What about the current? Okay, so for the current you will actually see that it's basically the current is basically, as soon as you connect the circuit, you have 10 volts here and you have 0 volts here, right, in the initial circuit. So definitely you will have a current here, right? And that current will be, you can use Ohm's law here. So that current will go through this whole circuit. So that will be I initial will be 10 volt divided by, so this is because 10 minus 0 divided by, so these 2 points divided by 1 kilo ohm. So at the volt divided by eta, so you will have 10 milliampere. So the initial current is 10 milliampere, and the final current, well, I have actually already written that the final current is 0 ampere. So here is IF equals to 0, and if we write out the values here, we have 10 milliampere plus, so I'm just writing the, sorry, I made a mistake here, the final current. So the final current is 0 here. So the final current is 0 plus the initial current was 10 here, minus 0 e to the power minus t by tau. Sorry, the tau was 10 to the power minus 3, and so this will be 10 e to the power minus 1000 t. And if you plot this graph, you will see that this graph looks something like this. I of t here, this will start from 10, so this is milliampere. I should write the units here. So this is, and this is in volts, right? So this is like 10 milliampere, and it starts from there and drops down almost to 0. It almost reaches 0. Okay, almost like that. So, and you can match this with the simulation results. For completeness, let's show another example, this time with an inductor. So the circuit we have used for inductor was something like this, 1 kilo ohm here. We have a switch and we have an inductor, 5 Henry. Yeah, and we are closing the circuit at t equals to 0, and that's what we want to study. And we want the expression of the current. So maybe use another color here. What's the current through this inductor? So, well, the expression will be I of t equals to the final current plus initial current minus final current e to the power minus t divided by tau. So first of all, what's the value of tau here? Well, because we are using inductor, the equation will be L divided by R. Okay, so the L here is 5 Henry and the R here is 1 kilo ohm, or you can say 5 Henry divided by 1000 ohm, and this is basically 0.05 seconds because Henry and ohms are both SI units. Okay, so that's the value of our tau. Now what about the initial and final current? So one thing about the initial circuit, you should always remember this is the circuit right after you have closed the circuit. Okay, so this is your 10 volts. Okay, let me change the color of the pen. So you have 10 volts here, 1 kilo ohm here, and you just closed the circuit. Okay, this is very important. So right when you close the circuit, so we usually write it like this, 0 plus. So right after we have closed the circuit, the current will be 0 ampere. This is because inductor doesn't actually let current to suddenly bump up to another value. It actually lets current gradually creep up to a value. Okay, so the current cannot jump up, and since this was initially 0 ampere and right now, just right now you have closed the circuit, the current will still be 0. Okay, so this is the initial circuit, but the final circuit will be something like this. The 10 volts, we have 1 kilo ohm here, and we have an inductor here, and like I have mentioned, inductor basically becomes a short circuit. Okay, so the current here will be 10 volts divided by 1 kilo ohm, or 10 milliampere. Okay, so this is our final. So this is our initial current, and this is our final current. So you just plop them into your equation. So I of t equals to I of f, which is 10 plus 0, the initial current, minus the final current, 10 e to the power minus t divided by 0.005. Okay, the whole thing milliampere. And so you have 10 to the power 10 minus e to the power minus t divided by 0.005, and you can write this as however you like. Okay, I'm not worried about that. So this is your equation for the time, and again if you plot them, you'll see that the current starts from 0 and slowly creeps up to 10 milliampere in this example. Okay, so that's the thing, that's the equation, and this is basically how we are going to do all of these problems, the transient analysis problems. So thank you.